I hope you guys are in the right room. This talk is about Scala 213 collections, and in general and in particular about a new collection called ArrayDeques. I actually recently learned that these things are called ArrayDeques, not ArrayDeques. Someone pointed me to a English.Stack Exchange link, which there was like a massive discussion what's the correct way, but ArrayDeques is the correct pronunciation. All right. So, about me, my name is Pathikrit. I work in a hedge fund located a couple of blocks away. I have been doing Scala for a bunch of years. Really love data structures and functional programming and how they can come together. As you may or may not know, that 2.13 has a lot of changes, especially the way collections are implemented. There have been almost a complete rewrite of the collections, with thankfully minimal API changes. So the upgrade shouldn't be that hard as is needed. But this talk I will introduce you to what's new and what changed, and in particular talk about ArrayDeques. So there's another talk by Stefan and Julian tomorrow where they'll be talking about migrating to Scala 213, and that would also focus a lot about the new collections. So I would try to keep this talk slightly different from that and talk in particular more about data structures and about ArrayDeques in particular instead of material covered by that talk. So what's changed? Huh?
It's today.
Sorry, it's today. So what's changed? So one thing that's gone is can build from. If you don't know about it, you're lucky. So this has been the joke of pretty much anyone who's new to Scala and points it out, like, haha, look at the signature of map. What is that? And there was a very good reason for it to be there, but we could have done it better. And now it's much simpler. This map looks a lot like the kind of functor maps that you're used to looking at. So that's one. A couple of new APIs. This one I really like. I'm not going to waste too much time going through the Scala docs saying these are the new APIs, but just telling you this one. This is one that was mentioned, and I really like it because I always find myself doing. So another things that's new are in-place mutable APIs. So mutable collections, if you want to transform them in place, filter in place, map in place without allocating new collections or getting new things back. So these are new things that's new. There are some more things. For example, streams are deprecated. There's lazy lists are the way to go. Views are first-class citizens. We put more views were like this weird thing that had bunch of corner cases and didn't really work properly, but now they should, and it's a really nice way to chain your code, write Fluent style code, and not have your runtime be multiple. It shouldn't traverse the collections multiple times. They got rid of the distinction between traversables and iterators. That was a fine distinction that very few people actually knew on the top of the head, which was to use when. The preferable, that's just iterable now. That's the single abstraction that you should keep track of. And there are some new collections. So specifically, I'll talk about one called ArrayDeques. This is a new collection in Scala 213. It's a mutable collection. Some people in the literature also refer it to as a circular buffer. So it can serve as a replacement for most mutable collections. And it's faster than an array buffer when used as an array, and it's faster than a linked list when used as a linked list in almost all the operations. This is also my first contribution to actual Scala. So woohoo. All right, thank you. So a little data structures 101. So as you know, there are two big flavors of linear data structures, arrays and linked lists. Arrays have this nice property that you can do random indexing. If you have 1,000,000 items, you can index into the 100th item or 10,000,000th item in constant time. You can update the ith item in constant time. So that's random indexing. But prepending to an array is not constant time, it's linear, because when you put something in the head of the array, you have to shift everything else to the right, and there you go, your runtime is linear. If you have a linked list, it's kind of the dual of the array in that sense, where you don't have a constant time random indexing because you only have a start pointer and maybe an end pointer, and you have to traverse and find the 100th element or the in 1,000,000 items. But prepends and appends are constant time because you can simply change where the pointers are pointing, and you can quickly insert things. If you actually have a pointer to the middle of the linked list, you could conceivably insert in constant time too. And to make a distinction, Scala lists is not a classical linked list because it's implemented as a const list, but that's an implementation detail. But in general, we have to make this distinction of choosing arrays or linked list for mutable data structures when you can't have best of both worlds. You cannot have constant time random indexing, but also have constant time deletes from the beginning or prepends to the beginning. So this is the chart. I would like to point out so ArrayDeques exist in Java standard collections since Java 7. But it has a couple of things that are slightly inferior to the one that is now in Scala 2.13. One, the actual random indexing is, for whatever reason, is a private method in the Java one. So they could have, and it is 0.1, but it's just private. I don't know why. There's like a long chain of discussion why. I don't understand why that even makes sense. Another thing is the insert and deletes. For a ArrayDeque implemented correctly can be made faster if inserts and deletes happen at the ith index. So the way the ones at least in the Oracle and the OpenJDK is implemented, it's actually linear runtime. The one in the Scala 2.13 is actually, if you want to insert some element at the ith index, is actually min of I and n minus I. So if you have 10,000,000 items and inserting on the 33rd cell, it's not going to actually move 10,000,000 items somewhere. It will actually move only the smallest possible chunk, in this case the 33 items left. So yeah, to recap, so apply, get random indexing, random index update, append, prepend, delete first, delete last, are all constant time. And insert and delete at arbitrary indexes are min of the index, and the n minus. It's a min of the distance of the index from the start or the end. All right, so why are they called ArrayDeques, not ArrayDeques? So some English I learned, so deque is actually the verb to say that you are dequeuing something, and ArrayDeques is not ArrayDeque because it's actually an acronym. It's an acronym for array double-ended queue, so that's what ArrayDeques are. And this is a very vanilla implementation of an ArrayDeque. The way it's implemented is you basically have a classical array underneath, and you have start and end pointers, which point to instead of, in a classic array, your start is the 0 and your end is wherever the size of the array is. In ArrayDeques, the start could be anywhere in the array and end could be anywhere else in the array. And the way to get an element or update an element, at the ith index, you add it to the start pointer and you do modular arithmetic on the length of the array so that you don't overrun, and that's how you index. So you basically offset from the start index. I'll have a better demo of this after this slide, so don't worry too much about it. So what about append? Obviously this is constant time because this is just math we are doing to index into an array. Append. So we have constant time append, because what you can do is you can simply add an element and increment the end pointer. And again, we're doing modular arithmetic here. Prepend. So this is the interesting one, because this is the one that is not a constant time in arrays. So for prepend, you can simply decrement the start pointer and update the element over there. I hope you're still convinced that doing this still keeps the update and apply semantics correct and constant time, and we still have constant time append, apply, append, and prepend. Similarly, delete last is trivial. You just move the end pointer back. Delete first is also easy. You move the start pointer to the right. Clear, you set the start and end pointer to the same location. And size is kind of cute. It's end minus start. Again, everything is done modulo n, where n is the size of the underlying array. And obviously, this is not the real implementation, because it doesn't handle resizing. It doesn't handle slicing and all the other operations, but this is a proof of concept implementation that would work. To better understand using a diagram, this is how an ArrayDeque looks like when you instantiate an empty one. You have a start and end pointers. They both point to 0. So in this case, I'm allocating a car ArrayDeque, and it allocates a small character array which all has nulls in it. So what happens when you append append a single element? So then we increment the end, we insert it at the start element and increment the end pointer. So the invariant is that the end pointer, so end is now 1, start is still 0. The end always points to the cell that is fillable next, and start always points to the first element that is actually occupied. Okay. Append a B, you see start goes to 2, and your array is filling up with 0, 2. And this is actually the indices of the ArrayDeque, and this is the indices of the underlying array. So, okay, C, D, E. So this is interesting. So I called, so this is what it looks like after I inserted E. So the first 5 elements in both the underlying array and the exposed API are A, B, C, D, E. What would happen when I try to call remove head, in this case remove head option, because it will return none if it's empty, would return the first element, in this case A, and increment the start pointer. So yeah, so remove head option returns A, and now the start is 1, end is 5. Your array still looks like this. Your ArrayDeque still looks like this. Your 0th element is B. If you do .apply B or .apply 0 or .get 0, it will return correctly the first element, which is now B, even though we did a remove head operation. So yeah, we just remove head is 01 and apply is still 01. So again, we're doing a remove head again. It pops off B, it pops off D. Now we're doing a prepend. So at this state in the array, the start is at 4, end is at 5, and we're doing a prepend. So what prepend does, it decrements the start pointer and fills that cell up. And yeah, so I'm not going to walk through every step, but you get the idea. So this fills up. So now the array is almost full, and we want to insert one more element. So I'm doing some more work. Right. So this is I'm demoing that if you do a remove head option when start and end are the same. So this is the condition when the size of the array is empty, which is end minus start, and they don't necessarily have to point to 0, because depending on your sequence of operations, you could end up with your start and end pointing to any arbitrary place in the array. So you do a remove head option, you get none back. All right, we're gonna append. So the array is almost full, and we want to append some more elements, and it resizes. Let's see. Right, it resizes. It goes from 8 to 16 elements. And this resize is incredibly efficient. During the resize operation, it will at most do 2 mem copies. If end is greater than start, it would just select the slice of memory from start to end and put it in the new array of double the size. Or if this is a wraparound case, it will mem copy from start to the end and from end to the last element. This uses Java's array.copy, which in most systems actually is a mem copy. So this is really fast, so you don't actually go one by one fill up the cells. So yeah, we resized and some more operations, append, prepends, so on and so forth. We're appending more cells. And yeah, so now we want to call clear. So again, what clear does, it simply sets the start to the end. So when I call this, start and end is 17. But there is actually currently a bug. You need to actually go and clear out all the cells, because else you'd be holding references to the memory. And that's a bug that actually exists even in current Scala collections and mutable collections, where if you call clear, it will actually hold references unless it gets unless the mutable reference itself is thrown away. But so here the way to do it is, okay, you set start to end, and you have to actually do another mem copy or mem set to fill up the array with null, so you don't actually hold references. But you see, there's a problem. We started out with an array of size 8, and we hit clear, and we're stuck with this 32 size array. So this is a memory leak, and it's not clear which API, should we resize it down, or imagine you have 1 million items and you call clear on a mutable collection. Should we resize it down to 8 items? Because what if you wanted to start adding things again? You need to regrow the collection. It's not clear which one is the correct. So there are 2 APIs now in 2.13 ArrayDeques. You can call clear, which does not resize the collection. So this is for a use case where your collection is growing in unpredictable ways, resizing, so you don't want to repeatedly allocate 8, 16, 32, 64, so on and so forth. But if you do actually know your use case, like, hey, I want to clear out back to the original default size, there's a new API called clear and shrink. So this would actually, this would actually shrink it back to as if it was the initial empty array call. So that's all the diagrams I had. Okay. So yeah, if you look at the actual source code of ArrayDeque, this is much longer than those cute 20 lines I presented. And there are reasons for that. One is, as I mentioned, we optimized almost all the operations by using array.copy, which is a memcopy underneath, which is fast on most CPUs. So if you insert at the ith index, as I said before, we figure out the smallest chunk to move, and we do that. Clone, again, is using at most 2 array copies. All the slice operations are using array copies, so at most 2 array copies to achieve all this. And this needs a lot of correct pointer array copy code, which that long code is. Another thing that we do to make it fast is to do preemptive allocations of the correct size. So imagine if you have a mutable array deck of size 100 and you're inserting 10 million items. As implemented, as the Scala interface has the default implementation, it goes one by one inserting. So you do repeated resizing. You would resize to 128, then you resize to 256, and so on and so forth. But you could do better. If your right side is not a traversable once, you can traverse it twice to figure out the size, or if it has O1 size, you don't even need to traverse it. And you can preemptively allocate the underlying array of the correct size and just do another mem copy from the traversable that you're pending or prepending to fill in that array in effectively constant time. Another trick, this is a really cute trick, which is if your size of the array is a power of 2, you don't actually need to do modulus using the mod operator. You can actually use a bit trick. So if n is a power of 2, then I mod n is actually I bit and with n minus 1. This is cute. So these are some benchmarks. I'll point to a GitHub repo which actually has slides of GIFs of operations benchmarks comparing array buffer, list buffer, and ArrayDeques with the size of the array as one axis. In almost all cases, ArrayDeques are incredibly faster. The prepend, as you can see, it's a millisecond in ArrayDeques, and the same operation takes 10 seconds, 9 seconds in array buffers because of this trick. And this is obviously averages of some benchmarks that I ran, which looks at various, it does some various random operations. The only thing that is slower is the random indexing. It's slightly slower because in array buffers, you can actually just random index. Here, you are doing some modular arithmetic. You are adding the index to the start and then doing mod. So, but I don't think anyone would ever notice that. I would also like to give a shout out to this ref tree library. I used that to generate that diagrams. I didn't actually spend hours making those images. I wrote code to generate those images. So it's really cool library. This is all the code that I had to write to generate those images, which is pretty cool. It comes with little utils, which gives you access to the private fields of any data structure. So here I'm getting out the array, the start, and the end indices, and then I can choose how to render it, and then I just do my sequence of operations and call render, and it renders and it generates those PNGs for you. This source code is, I will have a link to it. It's on GitHub, and you can check it out after the talk. So some takeaways. Please contribute. I thought contributing to Scala is kind of cool and scary, but now I think it's just cool, not scary anymore. It's way more accepting of new code contributions than some other languages like Java. I don't even know how to do that, contribute anything to there. And there's a lot of scope. There's a lot of things that we can improve. I love data structures and collections, and that's where I found my way to contribute to Scala, but please do. And since we have a major version change coming up, there are things you can do more influence than others. In general, I think data structures are cooler than algorithms. The reason being that it's incredibly hard to write a general purpose library which has algorithms which everyone can use because everyone needs some custom use case. But data structures you can write in a generic way and make it a library that people would be able to use, especially since the Scala standard library gives you interfaces like traversables and iterables and map-like. So you just have to implement them and maybe add some few new methods, and voila, you have some new data structures. And there are a lot of cool data structures out there. ArrayDeques was the contribution in 2.13, but you can check out a lot of functional data structures or even non-functional data structures from your algorithms class. Visualize your code. As I said, the ref tree library is really cool. You can write 20 lines. It comes with visualizations for any case classes, any data structures, or you can write custom ones like the one I did. 50 lines of code, and it generates beautiful animation, which makes for good presentation. And yeah, Scala 2.13 is around the corner. Please check it out. If you're a library author, try building against it and see where that goes. Else, yeah, just try it out in a small sample project. So that's my talk. That's the link. You can check out the source code to generate the visualizations. You can check out the source code. It actually has a minimal implementation of ArrayDeques that you can drop into your Scala code today in 2.11 or 2.10 or 2.12. It also has the benchmark code. One last thing is, this is the recruiting slide. We're hiring. I work at a hedge fund located 2 blocks away. We do a lot of quant trading, data science, functional programming, Scala, Spark. If you're interested, come talk to me or send me an email at this address. But yeah, that's it for now. If you have any questions. The question was how more about the benchmarks. What was it benchmarking? So the benchmark was doing fuzzy operations, like starting with an empty array or a small array of size 100 and doing a lot of random deletes and insert and prepends, and then doing an append and growing it up to a size of 10 million and taking averages on the way up for all the data structures involved, and running it over and over and doing a JVM warm-up before. And the default implementation, I believe, starts with a internal. If you create an empty one in Scala 2.13, it allocates of size 16 underneath. And that's the one Java 8 allocates, I think, and I just used that default size. I didn't do too much research on that. So, yeah, the question is, when you actually resize, how long does it take? I mean, if you actually do the math for random sequence of operations, you can actually mathematically prove that it's amortized constant time. But to do the actual resize, when you go from 128 to 256 elements, there are only 3 steps involved. You need to do memory allocation of 256 elements, and then you do 2 mem copies. So mem copies are, most CPUs have very native instructions where you can say, given this memory indices of start and end, and these other start and end memory indices, copy this data set there. So the way ArrayDeques are implemented, you can do it using at most 2 mem copies, most operations. So if you actually check out the source code, that's what all the operations do. They just do 2 mem copies, even for clone, copy, sliding, slice, I forgot other APIs. They all do at most 2 mem copies, including resize.
So it always doubles the size of it?
It always doubles. That's a good heuristic that many other data structures use. And it also makes the modular arithmetic very cute. All right. Thank you.